A lot of pop science outlets give a certain summary of quantum computing that I can almost guarantee leads to misconceptions. The summary goes something like this. In a classical computer, data is stored with bits, some sequence of ones and zeros, but in a quantum computer, you are able to represent every possible sequence of bits of some fixed length all at once, in one big thing known as a superposition. And sometimes the implication of these summaries is that quantum computers can be faster by basically doing whatever a classical computer would do, but to all of these sequences in parallel. Now, this does gesture at something that's kind of true, but let me see if I can prove to you why I think this leads to misconceptions, and I'll prove it using a quiz. To set it up, I want you to imagine that I have a mystery function, and I tell you that there's a certain secret number among all the numbers from 0 up to n-1, where if you plug that value into my function, it returns true, but if you were to plug in any other value, it returns false. And let's say you can't look at the innards of the function to learn anything about it. The only thing you're allowed to do with it is just try it out on numbers. The warm-up question is, how many times, on average, would you have to apply this mystery function in order to find the secret key? Well, if the setup was in an ordinary classical computer, there's really nothing better that you can do than guess and check. You go through all the numbers, and maybe you're lucky and find it early, maybe you're unlucky and it doesn't come up until later, but on average, with a list of n possibilities, it takes 1/2 of n attempts to find the key. Now, in computer science, people care about how runtimes scale. If you had a list 10 times as big, how much longer would it take? And computer scientists have a way of categorizing runtimes. They would call this one O of n, where that big O communicates that maybe there's some constants like the 1/2, or maybe some factors that grow slower than n, but the factor of n is what explains how quickly it scales as n grows. If n goes up by a factor of 10, the runtime also goes up by a factor of 10. Now, here's your quiz. For the equivalent of this setup, but in a quantum computer, what's the best runtime for finding the secret key? I've asked a variant of this quiz many times in a certain lecture that I've given over the years, and the options I typically offer are O of square root of n, O of log of n, O of log of n, and O of 1, where here O of 1 would mean that the runtime is just some constant that doesn't actually grow as n grows. Now, to be fair, I have not defined quantum computing. In fact, doing so from the ground up is going to be the goal of this video. So without showing you what this mystery function would look like in that setting, it's kind of an incoherent question. But it's not really meant as a quiz that I'm grading you on or anything. It's just meant to be a gut check of intuition before we dive in. In principle, it's the same task, finding a needle in a haystack where you want to discover which value out of many options uniquely triggers some function. I asked this as a YouTube post last month, which 100,000 of you kindly answered. The most recent time I gave it live was to a group of Stanford students. I also posed it to those attending the International Math Olympiad, and in all of these and many other instances, the answer distribution looks very similar. The most common answer is always O of 1, and this is wrong, and I'm pretty sure that it stems from that misleading summary. That summary implies that you would put all of the n values that you need to search into this mysterious superposition, and then you would process them all in parallel, and then somehow the answer would be revealed. The second most common answer is typically O of log of n, and this is also wrong. You would call this an exponential speedup. For example, if you increase the size of the list by factors of 10, an O of log n runtime would only tick up by the same additive increment each time. Now, this wrong answer, I suspect, stems from a misconception about how much better quantum computers are in general. There are very certain special problems where you can achieve an exponential speedup. The most famous case is probably Shor's algorithm for factoring large numbers, but most problems are not like that. In this case, the correct answer is O of square root of n. And this is a lot more representative of the typical speedup that you could get with a quantum computer. In 1994, it was proven that a quantum computer could not possibly do any better than O of square root of n on this task. And then 2 years later, Love-Grover found a specific procedure that actually achieves that runtime. So searching through a bag of 1,000,000 options takes on the order of 1,000 steps. A bag of 1,000,000,000,000 options takes on the order of 1,000,000. This big O actually hides something that's pretty fun, which is the constant of pi-fourths in the precise runtime, and that pi has its own whole fun story to tell, which I'll get to later. You might think that this puzzle with a mystery function triggered by one specific value is super contrived. But I want you to keep in mind this is meant to be a generic stand-in for any problem where you know how to quickly verify a solution, even if you don't know how to find that solution in the first place. This describes an enormous class of problems in computer science known as NP problems. So while a square root speedup is frankly not as earth-shattering as an exponential speedup would be, and while big O runtimes are often a lot less important than other practical considerations, it is thought-provoking that something like Grover's algorithm is even possible at all, providing this catch-all method for speeding up any NP problem. My goal with this lesson is to build up to a step-by-step walkthrough of how that algorithm works. It's actually very geometric and very beautiful. But we need to build up a lot of background in order to get there. The first 2/3 or so of the video will be spent building up the fundamentals of quantum computing, not with a set of analogies, which as we've seen can lead to misconceptions, but as a piece of math, which I think offers you a pair of glasses through which you can see a much more honest depiction of the whole field. This is one of those topics that has a few premises that are just going to feel a little bit strange at first, and I should warn you they take a little getting used to. My current plan is to follow this lesson with another one about some of the underlying physics, which hopefully can help motivate a few of the odd-looking rules that you'll see here. But today, the goal is to provide the minimal viable path to seeing a genuine bona fide quantum algorithm. Let me pull up again that contrast between classical computing and quantum computing, and let's see if we can build up something of a more representative mental model. It is true, of course, that data in a classical computer looks like a series of ones and zeros. And at a higher layer of abstraction, that might represent an actual data type, like an integer or some text. And at a lower layer of abstraction, those ones and zeros represent some actual thing in the physical world, like voltages across a capacitor or something like that. Now, these same layers of abstraction provide a pretty helpful framing when we discuss quantum computing. Over there, there's also some underlying physical measurement, and again, you represent the outcome of that measurement with some sequence of ones and zeros, and again, this might implement some actual data type that you care about, like a number. This symbol that I'm showing, by the way, is called a ket. I'll explain it properly in a couple minutes, but for right now, just think of it as conveying that something is coming from a quantum computer. Let's start things off with a description of quantum computing through the lens of that middle layer of abstraction, meaning we're going to postpone all of the underlying physics for now, which is a little bit like teaching computer science without discussing hardware. In a classical computer, there's no need to distinguish between the state of memory and what you read out from the memory. Both of them just look like the same sequence of bits. But it's a very different story in a quantum computer. Our main job today is going to be to understand something called the state vector, which is continuous. This is the thing the computer actually operates on, but it has a very unusual relationship with the values that you actually read out, those discrete sequences of bits. Before I can define the state vector, you need to know one other key difference from classical computers, which is that this value that you read out, which again just looks like some sequence of ones and zeros, is random. Or to be a little more accurate, I should say it's typically random. The way you can think about this is that if you run a program on a quantum computer, that program doesn't necessarily determine a particular output. Instead, it determines a probability distribution across all possible outputs. So for the example I'm showing on screen, this would be a very small quantum computer where the thing that you read out has 4 bits, meaning that there are 2 to the 4 or 16 possible outputs, and the specific program you run determines some kind of distribution across all those possible outputs. Some programs might manage to concentrate more probability on just one of those outputs, but other programs might give a more even spread across everything. This example, by the way, where the thing you read out has 4 bits, would be called a 4-qubit quantum computer. And more generally, if you have a k-qubit quantum computer, that means there are 2 to the k distinct possible outputs, and any program gives a distribution across all of those, and the thing that you read out has k distinct bits. That word qubit, by the way, is another thing I'm going to define more precisely in just a minute. I do want to emphasize that this distribution is implicit. You never actually see it directly. You instead infer what it must be based on the program that you run. You never see all bit strings coexisting at once in some kind of way. You just see one of them, drawn at random, according to this distribution. At a lower layer of abstraction, what I'm describing as reading out from memory looks like a physical measurement, and the randomness stems from the laws of quantum mechanics. If you're curious about the physics, that lower layer of abstraction, that's exactly what the next video is for. Up in this layer, you just think about probability distributions over all possible bit strings. Now, one more funny rule here, which does bubble up from the underlying quantum mechanics, is that after you read out from memory and you see some particular value, the underlying state of the computer changes such that now all of the probability is concentrated on whatever value you read out. So if you kept reading out from memory over and over, you would just keep seeing that same value. You might imagine these programs as creating a very delicate and sensitive probability distribution, where the moment you look at it, sampling from that distribution, the whole thing collapses to one value. Now you might be wondering, where does this distribution come from? This is both the most important and the most confusing part. You think of the state of the computer as being described by a big vector. Right now, when I say the word vector, you can just think big list of numbers, although as you'll see later on, it can be helpful to think of this as a direction in some super high dimensional space. Each component of this vector corresponds to one of the possible values you might read out, one of those distinct bit strings. So in this example where what you read out has 4 bits, the state vector would have 16 distinct components. The state vector is not the same thing as the probability distribution over all possible outputs, but it is very closely related. The fundamental rule, which I admit is going to look very strange at first, is that if you take the magnitude of each component in that state vector and you square it, that gives you the probability of seeing the corresponding output, the corresponding bit string. Let me just say up front, a lot of people learning quantum computing find this state vector a bit weird. What is it actually, and why are we squaring things to get probability? As it is, for the sake of simplicity, there's a certain important detail that I'm neglecting until the end of the video here. I just want to flag that for most people, this takes a little getting used to. And to be super clear on what I mean with the fundamental rule here, let's suppose that after this program processes this vector, maybe the component of it associated with some specific bit string, like, 0011, happened to be 0.5. Then when you square that value, 0.5 squared is 0.25, so the observable implication of this is that when you read out from memory, you have a 25% chance of seeing that bit string, 0.